Excellent.
Okay.
Now you can start.
Great. Mhm. Oh, sorry. Okay, great. So let's get started. So my name is Alexis Solovis, and I work as a data scientist at NVIDIA. So, and I will be providing some basic stuff about mathematical modeling, a little bit of neural networks, and some kind of programming that could be implemented for uh, uh, for for mathematical modeling. Okay, so first of all, I totally realize that you may not understand me in full. So if this happens, please raise your hand. I believe in Skype or I'm sorry, in Zoom, there must be some. Hey, stop. Is it a raise hand option here? I believe that must be. Oh yeah. Great. Good. That's great. Okay, so if you want to stop me, so please do this. Exactly, because as from the previous lesson, I found out that not everything was very good. Okay. Okay. Just give me 2 minutes and let me get prepared. Mm, okay. Just okay. So so before we get started, uh
If you need some time to prepare,
yeah, yes,
I
please.
can I
Actually, I
can
need 5 minutes
send.
to complete the notebook and have everything nice
No, I
as
won't
per
take
usual.
5 minutes. I don't know what to say during five
Okay,
minutes, but
two
I can
minutes.
just show show the people. If you're watching us, if you're connected from your laptop or computer, then there is this control panel of your connection of the Zoom, and then there you have reactions. Uh, in English, it's reactions, and then there are such reactions as slow down. For instance, if it's too fast, if the speaker is going too fast, you can just press slow down so he can see that, or I will see that he needs to slow down and tell him that. Or if he's gotten too boring, then you can press another button which says speed up, and then we'll tell him that he needs to uh, um, not to be so boring. There are also like you can vote like yes or no. For instance, if there is a question, was everything clear? And you say yes, it was, or you can say no, it wasn't. If there's something, there are also other reactions, but these are the main ones, the most important ones. And of course, raising hand. Uh, we don't need to raise hand. Actually, there's quite a there's not so many people with us right now, so you can simply turn on your microphone and tell whatever you think, whatever you want to say. Uh, that's it. So feel free to stop us, to accelerate us, to somehow make us ask us to go slower, because all this is for not for us but for you. So it's very important that you understand everything that's going on, uh, because we expect actually that you do some exercises yourselves. I mean, that's the whole point. I mean, the whole point is to teach you to do something on your own, not just look how Alexei or Ray uh, knows how to do something, but also learn to do it yourselves. Um, SO is back. So is it Sophia, right?
Mhm.
No, she's gone. Okay, so I'm gonna lower my hand right now. It also needs to be done on purpose. And Alexia, are you ready?
Oh, give me 2 minutes, please. Almost
Okay,
ready.
okay. Uh, Andre, maybe some amusing 2 minute speech from you.
I think it's not necessary. No, if something will
Just
go
wait.
wrong, I will speak something. No, I
Okay.
think if some. Oh, okay.
So let me get started. So let me share my screen, and we will get started with the repetition of the previous topic that was Game of Life from Conway, and we will do some statistics. Let me start. Oh, but it looks. Oh no, I have it. Just a second. Share screen. Select window or screen. Okay, it looks like I'm sharing my screen. All the stuff we will be doing, in the Python notebook, and Jupyter. So let me get started. Here it is. So I believe that you do see my screen. Oh, let me open it in a different location. Okay, our topic for today will be also dedicated to the game of life, and we will be doing it in a Python notebook. So you can do it locally, or you can write it down in Collab. That is just collabresearch.com. Okay, so let me open it here. Yeah. Oh, no, it's already. collabresearch.com. So we can create a new notebook. So if you have a Google account, you can easily connect to it. Okay, I will be working locally only because this is a little bit faster. Okay, let me reproduce the notebook that we had on the previous class. Okay. So this now the generic class to simulate the automator. Okay.
You've just copied code from some source. Is this source
Yeah.
available for all students? I mean, or should they take it from you, or should they write it
Oh,
themselves?
we will be. Yes, this source is some kind of available, but let me create the notebook that you will be using. So we will just how to say, we will
So all this
modify.
will be available for the participants of our workshop, right?
Yes, of course, sure.
Okay, okay. Just to know
Okay.
if okay.
So let's get started. So lifelike cellular automation. I don't know how familiar you are with this code. Should I explain, or is it okay to go ahead? I mean, what does this strange stuff mean? Hello? Is anybody here? Or we have problems with the net?
We have no, we don't have problems, connection problems now, but we have a reaction from Stefan that who says that he understands the code,
Oh,
and
that's great.
no reaction from others, but hopefully they understand it too. I don't understand it, so I'm not the right person to be asked about it.
Okay,
It's
that's good.
just transfer from
So this is
silent
just
to
some
English.
manipulation with matrices. Actually, not with matrices, but with tensors. Uh,
Now
and
I do understand it. Okay.
so this is n is a tensor with a certain shape, and it's kind of a convolutional kernel. Okay, so okay, so let me create the different rule. So let's play with different rules. Oh, it doesn't work. What's going on? Okay, let's create this one. C0. Yeah, good. Yeah, nice. Okay, so let me explain one more time what is the meaning of this B1 S123. So B1, it means that the new cell is appearing in case of there is one neighbor, and S123, this is about survival. Okay, so we are starting from the top left corner. Let's get started from the middle. Yeah. Let's see what's happened. Here it is. One more time. Okay, does it make sense? Okay, let's a little bit change the rule. Okay, you see it becomes more sparse. Or this, it becomes more dense. It should be. Okay, so the purpose of this topic. Okay. So this whole stuff is live cellular automation. Okay, so let us do some stuff. Oh, it will not work in this way. So let us do some graphs as we did in the previous ones. So for the graphs, we definitely need for the mathematical modeling. So this is just an observation of what is going on, how it works. Yeah. So you see there is still some dynamics. So let's. So here is a different one. Okay, so this is just you are observing some process that starts here, that goes here, and the rule is this, so it should be more dense. Or it will be very dense. Okay, so to create some graphs, we need to keep the statistics. So to keep the statistics, so on the iteration phase, and here is this iteration phase, yeah, we need to fix something. Okay, am I here or I am? Yes, I will be checking statistics, stats. Okay, so they will be living cells. Okay, let's get started with just the number of living cells. I think it should work. Okay, here it is. So let's, for example, so the classical game of life is this. Yeah. So let's iterate it to. Okay. Yeah, that's nice. So looks like. Okay, so let's observe this, I don't know, dynamics, statistics, how it lives. Let's do more iterations. Okay, so let's wait for the end and let's do some information. let's calculate some statistics. Okay, good. So we have the following graph. So here it is. So when you are creating graphs, it's nice to have a title. Through time. Or it's better to be generation. Now it's better. Okay, so this is the number of living cells. Now let's figure out, is it supposed to be static or dynamic or whatever? So let's first of all increase the population. Not increase the population, just by increase the okay. So you see, it becomes static. Absolutely static. Yeah. So it becomes this. Well, so this is the number of 37.
Not the picture itself, but the number of living cells, right?
Yes, this is the number of living cells. So you see,
Okay.
this is the stability, kind of stable stuff. Yeah. Okay. Let us figure out what would happen for the different rule. So this is for the living cell, and this is rule equals to this one. Rule is rule. And here, living cells, label, rule. So we will be studying how the number of living cells at the end and the statistics will depend on the rule of birth and of survival. So let's wait. So let's get faster. Maybe this. Here it is. Okay, done. Okay, so label should be rule in this way. Yeah. So this is the dynamics for this rule. So let's figure out what will be the dynamics for the different rule. Okay. And these living cells. So let's do it not a list by a dict. Okay. Rule. Okay, ready? Mm-hmm. Okay, now let's do it for all the rules in living cells. Do you understand what I'm doing? By the way, this is a question. Yes? No?
Yes.
Good. Okay. Okay, that works.
I still don't understand why you're doing it. I mean,
Oh, I'm
what are
doing
we?
it
What's
to
our?
demonstrate the different dynamics of how this stellar automata works. So it starts with a certain number, then express some dynamics, then it becomes this. So let us do this same thing for kind of different rules. Okay, here it is. Let me do it one more time. Mm-hmm. Good. So let's create a different rule. Survival 1, 2, 3, for example, 4, 5, 6. So it should be more fractal-like. Okay, good. You see? This is one more. Okay. Let's keep 2, 3, 4. Okay. A different one. Yeah. So this is birth to survival 2, 3 is this. Survival 2, 3, 4 is this. So you may definitely assume that survival 2, 3, 5.
However, 2, 3, 4 didn't stabilize. Does it matter?
It does. It does stabilize. Here it is.
Well,
Approximately.
we have, well, approximately, yes, but we have some
Yeah,
fluctuations,
yeah, of course.
minor fluctuations.
Yeah.
So we don't pay attention to minor fluctuations, right?
Yes, that's right. Yeah.
Okay.
So if you can see, yes. So these fluctuations are, so this is kind of the periodical function. So if you see 4, 2, 3, 4. So let's see 2, 3, 4, 5. Here it is. It's more stable. And the graph is definitely like this. Yeah, you see the red one. Okay, let's not do this. Enough with this. Okay, let's change the birth rule. So now birth is 3. Let's do birth 1, 2, 3 and survival also 1, 2, 3. It should be highly periodical. You see? Okay. Here it is. This is also very stable. It becomes stable and it is alive. Okay. Let's decrease their survival. How to say? Let's survive if only 2. So you may see that their stability function will be lower. Here it is. You see? Okay. I hope this makes sense. Well, actually, for drawing graphs, I absolutely do not remember of how to fix this axis, everything else. So I ask this guy. So setting axis limits matplotlib, and it usually tell me, okay, that's great. Set x lim, set y lim. Yeah. Okay. So let me copy paste this because I don't remember. From 1 to 500, and I believe for y lim it would be similar, from 0 to 6,000. Oh, it's y. It should be y. Okay. I also don't remember how to create big graphs. Okay, great. This is this way. PLT figure. Let's get it bigger. Oh, too much. Okay, now it looks better. Okay, so what may be the problem that you will be facing somewhere? For example, prepare I don't know, research how something behaves in case of I don't know. So let us set in case of some corner cases. So for example, let's be so okay. Let's do one more game. For example, the rule will be both 3 survival 3, 4, 5, 6. I believe it should be all dead. No. Okay. This one, somewhere to the top. Okay. So the question that you may be facing could be that given some dynamics, given some statistics. So this is about the, I don't know, epidemic or bacterial or something like this. So create a system or research a system with some certain dynamics. Let me introduce. So yeah, and you can definitely change the rules here, and you can do whatever that you want. So the cellular automata is good for modeling in here. So, and it is definitely sufficient to do here. So if it is possible, it would be great if I can give you a kind of homework just to have a try. So try to reproduce this, what we are doing here, and additional stuff. So you see here, there's only black and white, nothing else. Yeah. So black is means that the cell is occupied by a certain is occupied by the cell, and white means that this cell is unoccupied. Okay. So let's create some how to say, antibiotics kind of, or maybe fungi, or maybe predators, whatever. So the cell could be occupied either in the cell could be occupied, so here the cell is occupied or unoccupied, so it is 0 or 1. So now let's figure out that the cell could be occupied with the organism of the level 2. 2 means I don't know, higher species, predator or heterotroph or whatever. So it's like grass, rabbits, and wolves, something like this. So here is only grass, nothing else. Okay, so try to change this code to create grasses, to create another. So you can see that it is binary. Yeah. Oh, sorry. Yeah, so this is binary. So we will create something that should be not binary. Okay, so let me send probably this notebook to our to here. So can I, yeah, the question in chat. Okay, great. Uh, well, Vladimir, can I send this file somehow to you or to the
You
chat?
want to send the file?
Yes, exactly. So this is just a file. This is the
Okay,
program.
what am I supposed to do with that file? Should I send it to all the
Share.
participants?
Yes.
Share the. You can try. Yeah, I believe you can try just sending the file via the chat. Just
Oh,
drop it there.
okay. There, the Zoom chat.
Yeah.
Is it possible to send files? I wonder. Text. Yeah, it does. Okay.
I believe that drag and drop would also work.
Yeah, I did. Game of Life 2. Okay. So now probably let's continue. So this is just a cellular automata example. So let's probably get do some more stuff with the real mathematical modeling. So let's start with the physical model. Just let me check.
Just one question about this file. Is it like a
Yeah,
file for the homework? Well, or
yeah. So this is,
are they
and
supposed
let me write
to
down.
download
Okay,
it
homework.
now? Okay.
Let me print it. So homework optional, of course, as usual. Try to create another species on the land of level 2 and set the rules. So for level 1, it will be something like B23 as 2, 3, 4, 5, 6, 7. And for the level 2, there should be something like B. So let's say so B. Where B is number of living cells of level 1. B is number of living cells level 1. S, number of not living cells. B is the, how to say,
birth.
is the predicate of birth. Yeah, predicate of birth. If number of living neighbors of level 1 is the following. C is the predicate of survival. If number of living neighbors is neighbors of level 1. Okay, let's introduce AB, let it be D or BB, or I don't know, let it be D. Will be predicate of birth of level 2 if number of living cells of level 1 is A, B, C, D. Let be E, predicate of survival if number of living cells of level 1 is the following. So, and level 2 overrides level 1. Does it make sense?
Yes.
So there are 2 species. I don't know, rabbits and wolves. So wolves, they eat rabbits, and rabbits are just and wolves, they don't care about the number of other wolves. So of course, if wolves ate all rabbits, they will not survive. Does that make sense? Because there will be no living neighbors of level 1. So all living neighbors will be another wolf. So the creatures of level 2. Okay. So for the rabbits or for the living cells of number 1, the only problem is overpopulation or underpopulation. So, and balancing with B and S values, constants of the model, you can see the different stuff. So now we include one more species of level 2. They will be wolves. So for the simplicity of the model, let us think that these wolves, they act like an ideal gas. So the wolves don't see other wolves. So they see only rabbits around them, and the population of the wolves depends only on the population of the rabbits nearby. Okay, so if you see the, so this is the forest with rabbits with So it could be a very small number of rabbits, a big number of rabbits. Anyway, but the number of rabbits is pretty stable. It may fluctuate, but it's still pretty stable. Oh, of course, it depends on the starting condition. Here are the starting condition. So I just defined here, but you can see that it becomes pretty stable. So let us add one more species. One, just one more. If you want to, bonus problem. Add predator, or it's in biology it doesn't call predator, it's carnivorous. That is predator of level 2. So predator of level 2 may eat both rabbits and wolves. So that's why DE, so the FG, that will be birth and survival rates, will depend on the number of living, neighbors, regardless of their level. Yeah. So it means that B. So rabbits just look, just watch other rabbits, and they don't see wolves. Wolves see rabbits, and they also don't see wolves. And predator number 2, I don't know who are they. I don't know, eagles. So they see both rabbits and wolves, and don't see anyone else. So of course, color them into 3 different colors, and definitely draw the survival curves on the same graph. Bonus problem number 2. Try to create the rules that perform a long-term dynamics. Long-term dynamics means periodical function with a period of, say, 50 generations. Does that make sense? So this is a very big homework, really very big. So it may take, I don't know, maybe 1, 2, 3, 4 hours of programming. So it's not only real programming. So it's a kind of, it's a research. So if you can perform this research, that would be awesome. Okay. Okay. I just want to ask Vladimir one more thing. How much time do we have more? So do we have 15 minutes more, or maybe half an hour?
We have about half an hour.
That's great. Yeah, that's fine.
It's,
So
it's 10 to 8 here in Serbia. So we announced that will be done by 20 past 8. So we have half an hour.
okay, that's great. So in California, it's 10 a.m. So it's
No, it should be 11.
Oh yeah. I mean 10:53.
Oh,
11 will
California,
be,
when
yeah,
it's
11 will be in the
10:53, then it's 10, right?
Yeah, it's 10. By the way, do you have the time shift? I mean, so we will be having the clock turn in the middle of March. I mean,
Yes, same
there
here.
is winter time and summer time, 2 different times. So on 23rd of March, we will be having this change. Hello.
We will also have the change in time
Oh, that's great.
in March.
Okay. So actually, this okay. So I want to ask. Well, I want to ask Vladimir about Lotka-Volterra differential equation system. Should I explain it, or everybody knows it, or it is too complicated, or this is okay?
Why are you asking me? I mean,
Because you teach math. I am physicist.
but I teach math not to these guys. I mean, I didn't
Okay.
explain this model to my student. I mean, because
Okay,
we
no
didn't
problem.
even reach the derivatives yet. But I believe that many know derivatives and differential equations and everything. So I think you should
Great.
ask the guys.
Yeah, great. Okay. So what I want to do is to figure out this game of life, Lotka-Volterra, active equilibrium from the different perspective. Okay, so you do remember probably. So if you do the homework in the following direction, you will be great. So let me. So what it would be great, maybe just to have a. Okay, how to say, I believe Wikipedia will be sufficient. So what I want to talk about, it is Lotka Volterra equation. So Lotka-Volterra equation is also about rabbits and wolves. That's totally. But the bigger difference between what we did here and what we are going to do now is that for the game of life, there is a field, there is a forest, or whatever the ecosystem, and it is possible to have a lot of alive rabbits on one part and a lot of, I don't know, alive wolves on the different part. So now we will be talking about the point system. Uh, okay, differential equations, too complicated. But anyway, let's play a game with differential equations. So there will be Lotka, Volterra, toy example. Okay, so let's get started. Imagine, so let me explain a little bit. So there are two species. Okay, let it be not wolves. Okay, X is population of rabbits. Y is population of foxes. Okay, now dx over dt, where t is time, is the growth of rabbits, and dy over dt is growth of foxes. So this growth of rabbits means how many new rabbits are being born in this moment of time. Let me do some probably more explanation. So there So, and the Lotka-Volterra equation, X, is that the growth of rabbits is proportional to the number of rabbits and is proportional with the negative sign with the number of rabbits and the number of foxes. And the growth rate of foxes is proportional. Okay, let it be CXY minus DY. Oh, should I? Okay, so it is disproportional to the number of foxes. So you can see what is the meaning of the first equation. The growth of rabbits is proportional to the number of rabbits. So if you have an equation that looks like dx over dt equals to ax, the solution for this equation will be the exponent function. Yeah, so now we have these two different functions. So the parameters of this model is A, B, C, D. And we want to look what is going on with this function. So let's call these parameters. So what is A? A is growth. Oh, I made a mistake. So growth rate of rabbits. So B is death rate of rabbits due to predation from foxes. Oh, yeah, so this is so let me turn on light because there are people here. It looks like no one is here. Okay, A, B, C. So D is natural death rate of foxes, and C is a factor of how many rabbits are needed for the birth of new one small fox. Does it make sense? Guys, do you understand the meaning of these four parameters? Okay, so we have these parameters: growth rate of rabbits, death rate of. Oh, we suppose that rabbits are how to say, the only cause of death of rabbits is when foxes they eat them. So this is the only, how to say. Okay, so now let us do some Python programming, and to see, I will be a little bit copying, a little bit. Okay, so ODE int, it's ordinary differential equations. Okay, now let's do some simulation parameters. Okay, T is the timestamp. Okay, this is good. So this will be noise term. And we need the end of the simulation time. Okay, now let's create a time vector. Now, rabbits, foxes. Okay. Okay. Let me just copy paste the good values here. Birth rate of rabbits. Okay, what's going on? Time step.
First tier should be time step.
Oh yeah, of course. Sure. Yeah, thank you very much. Yeah. Okay, so let us set the initial conditions. So they will be 100 rabbits and 20 foxes. Okay, very good. So let's do the okay. So this is the actual simulation. Okay, so I will be using this. Let me copy this here. So for you to understand how to simulate the rate. Okay, so it will be xd derivatives will be x index minus 1 plus x plus what it should be, oh, times a minus oh, we can do this. So I just do this. So this is x. Here it will be a minus by. Yeah? So a minus b y I minus 1. Okay, so derivative of y is will be the same. So this is y, and here cx minus d. Yeah, y I minus 1 times oh, it's c. So it is cx minus d. Yeah. Oh, it's different. It should be this. Yeah, it will not work in this way. Okay, so now next calculate next x will be x I minus 1 plus xd. So this is the Lagrange theorem time step, and next y will be y I minus 1 plus yd time step, and now next x and y append next y. Okay, great. So, oh, I did it. Okay, plot it. So we did the simulation. Now let's look what's happening. So I set up here the initial population of rabbits to 100, the initial population of foxes of 200, and this is how they live. And I want to see how many rabbits are there, how many foxes are there. So what's going on? Okay. So let's I don't know. Let's start with this. What's going on? Did I forget? Yeah, PLT plot, of course. Okay. Oh, nice. X and Y have the dimensions TX. Okay. 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 And timestamp. Okay, now good. I hope you understand what I'm doing. T over X, T over Y. Then X. Okay. So oh, now it works. Good. Very good. That is exactly what I wanted. Okay, now let us create this graph in the, how to say, good way. Okay, so okay, just a second. So it is label or legend or name. So rabbits. Okay. Nice. PLT grid. And we want it big. Is it too big? Yes, it is. It's very big. Enough. So, and this is very good to say get the titles. So this is deterministic Lotka Volterra model. So This is time. This is population. Now it's very good. Okay, so you can see the number of rabbits. It's big, it's smaller, 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 smaller. Okay, what will happen if I set the number of rabbits to 10? There are too many foxes. You see? Okay, what if I say the number of rabbits is 5? You see, the same. But what if I say the number of rabbits is 2? It changes. Okay, let's do nice. Is it static slim? I don't remember. Maybe this? No. It did told me how to do it. Oh yeah, I see. Okay, and it told me it should be list. No. Ah, it's just X slim. It's not set X slim. Okay, yeah. Now it is very good. So, and the last thing is face portrait. Face portrait means how the how to say, how X depends on Y. So how number of foxes depends on number of rabbits. Okay, simple. So X, oh, not good. Let's create
Yeah,
it here.
it wasn't something I expected to see.
Yeah, this.
Yeah, that's more
this.
like it.
Say again. I'm sharing. Do you
I
see
said,
this?
I said that that's more like it.
Ah, yeah, this one. Let's do nice PLTX label. This is so on X we have rabbits and PLTY label foxes. Yeah, and PNT plot. Let's I don't know how to call it. Okay, let's say face portrait, because this is face, and let's make it big. Figure. Maybe this is too big. Oh, it's not plot face. I wanted to say title. Yeah. Let's color green. Yeah. Okay, here you are. Now let us do, for example, some game, some play, and this will be the homework. So let me show you what would change if I say, I don't know, make the model more rigid. So it means that I increase the death rate of rabbits due to predation 3 times more rigid. Okay, you see? Here, it's rigid, strict, I don't know, solid. Let's less it 10 times less rigid. Absolutely soft model. Absolutely. You see, rigid, soft, very soft. Yeah. Okay, so let's first of all let me share this notebook with you. Here, try example of Lotka Volterra. And if someone wants homework number 2, include predator number 2 to the system. I don't know. So there are rabbits, foxes, and someone who eat both rabbits and foxes. It could be eagles. Okay. So the only reason for rabbits to die is that foxes ate them. The only reason for foxes, there are 2 reasons for foxes to die. There will be 3 reasons for foxes to die: natural die of foxes, not enough food, and eagles ate them. So, and for eagles, the only reason to die is not enough food, and the reason for the birth of eagles is enough rabbits and enough foxes. Does it make sense? Okay, so actually this is for Vladimir and for Andrei. So what I'm trying to get forward is to get forward to the strange attractor. Actually, the strange attractor is a system of 3 differential equations with the typical chaotic behavior. Does it make sense? So the Lorentz model. Yeah, there are some nice pictures. So, but we will get started with the deterministic Lotka Volterra. In the future, we will add weather to Lotka Volterra. They could be cold winter or hot winter. So this is just a stochastic term to the Lotka Volterra model. So it becomes fuzzy. So we can see. But homework number 2 is, okay, questions. We're almost done, so 10 minutes to go. So is it too complicated? Nobody knows about this differential stuff. How can I do this? So actually the homework is create nice pictures. Create pictures that are colorful and nice and look like this or look like this. So I believe that you may not understand why the model becomes rigid. So, okay, for example, this will be extremely rigid model. Almost not differential. Yeah, here it is. Right angle. I believe this is too much. Let's do something like this. Why I changed the constant and the graph changes? Nobody knows. Okay, this is still pretty rigid. So this is still differential, but here the derivatives is very high. So it is rigid model. Like in heat pump machine, like in the cycle of the refrigerator. So it's cooling and heating. But this is from physics. But the equations are pretty the same. Well, okay. Questions? Is it too complicated? Does everyone understands everything? So actually we are here to learn mathematical modeling, and here are the 2 simplest examples of mathematical modeling: rabbits and wolves.
I have, if nobody has a question, I have a strange, maybe unpleasant question. Well, here we start from the equations, and knowing these equations, we make a computer code a program that predicts the behavior of the system. But shouldn't we start from some environmental description, from some physical or biological description, and extract, derive these equations from this description? I mean, Isn't this the most complicated part?
Okay, yeah, this makes sense for me. So you probably mean that here the equations are given. So
Yeah,
here
I
are
mean,
them.
to
We
create a
start from here.
program given the equations, I mean, it's
Mhm.
I believe that almost everyone here is capable of doing this. But how do you get these equations? I mean, how do you get the coefficients? How do you can make a certain number of observations? Then how to extract these coefficients from these observations? Why is it first order differential equations and not second order, and et cetera, et cetera? I mean,
It makes sense, makes sense. So actually, how to say, the short answer to all these questions is simplicity. So this is the model. This is as simple as possible. If you simplify this model, this will not work. So this is the simplest possible model. So that's why the first order, not the second order. That's why there are all terms to the right are linear, no non-linear. So everything is linear by two variables. Of course, it's linear by x and it's linear by y. The good question actually, and it is difficult probably to answer, why did I get this constant as it is? So why a is 1 and c is 0, 0, 2? Why it is not working on different constants, or it start working in a really weird way? Yeah, and this is definitely very good, Yoso. Thank you very much. So we will probably start next class with this. So having a biological system, or not biological, or a physical system, and having some random observations. So I see that every day in the morning it is bright. So this is the observation, and every day at night it is dark. This is also an observation. Can I build
or
the
for instance,
model
a fox
that
needs
describes?
to eat at least one rabbit a week in order to survive,
Mhm.
something like that. Yeah. Hmm. Sorry, I
Yeah,
interrupted.
yeah.
You were
So
saying, uh,
you have a strategic mindset. I'm
so you can explain how we can derive these equations and all the properties in them from such environmental conditions, right?
from the observations. Yes, of course.
Hmm.
Yeah, this makes
Good.
sense to me.
I think that should be interesting because what we expect to see on the competition and what the most fuzzy thing about modeling is how to write the equations.
Yeah, I
So,
totally agree with you, but I'm a little bit concerned and I want to ask the students. So, hey guys, are you familiar with all this Python code, what I'm doing with these graphs, with these grids, with this, I don't know, operations? So, what does it mean? NPY, arrange, what is this strange thing stuff? Append what to what? So, this is some Python code. Okay, I see. I see one. That's great. That's really great. Okay, because I'm a little bit concerned. I started with the Euler integration, and I'm not sure. All, please answer. Yes, please, please, please. Because I want, there are some strange things because, how to say, probably the physicist guys, they do know it. This is a Runge-Kutta equation, the leapfrog equation, the metropolis model. So I have started with the simplest one, with Euler integration. So you have, how to say, this is how to model the derivatives, how to model the change. Actually, derivatives is a change. It's like, I don't know, it's like doors in the elevator. So you open the doors by a little and you wonder what function is behind the door. And the simplest guess, oh, it's a linear function. Why it is linear? Because linear is the simplest function and I want to do it as simple as possible. So I don't do some predictor, corrector stuff. Difficult. too complicated, because if I start with this too complicated stuff, it will be more about differential equations, vector analysis. So it will be more about math, not about modeling. But from the other side, actually, because I'm doing this in a very kindergarten toy examples, the accuracies are not so good. The model are too simple. Well, so I need to find a balance between being too simple and being too complicated. And you are my only feedback for this balance. So please give me that feedback. If you give me oh, I don't understand everything, so that's totally okay. And let's spend 1 or 2 lessons just to find out what is Python, what is range, how to do lists, how to do everything. So my first thought was to get started with C, but I made a decision that we would better narrow down to the algorithms, not to the actual programming and coding and performance and all this stuff. So it is better to understand slowly than to make it faster. Because if you can do faster things and you don't understand what you are doing, this is much worse than you do things in a slow way, but you understand what is going on. So you understand the source. So that's why I really want you to create the homework. This is not a homework for you. This is a homework for me. So to understand about the level, to understand where we are. So it's like fitness training. So I go to fitness. If I take, I don't know, the dumbbell of 100 pounds, I will be dead. If I take a dumbbell of 20 pounds, it's too easy, too light for me. So I need to find out the weight that corresponds my strength. Does it make sense? Good. That's great. Okay, so Vladimir, I believe we are in time. Yeah.
Yes, I think I think that we should round up. If any questions, there is still time to answer them. If no, thank you all for
Yeah, no
coming.
problem. So please answer me questions or through Vladimir. So I'm always here. Anyway, let's meet in a week. It would be great. So I appreciate it. Okay.
So as far as I can see, no questions. So thank you all once again. See you in a week, and as
Okay.
soon as the recording is converted, I'll
And
send.
the notebooks are also here in the chat. Please share them or
Yes.
use them for something. Of course, you can find them in Google or similar in Google. So if you have internet, if you are not disconnected from the internet, you can find everything. Yeah. So
I think we should make like a query. Do they have internet? Does everybody have internet?
probably, yeah. Yeah. Okay. See you next time.
Fine. Thank you all. See you.
Have a good
Bye bye.
week. Bye bye. Oh, have a good
Thank you
night.
all.
Yeah. Have a good day. Yeah. Bye.
Yeah.
Thank you. Bye.
Bye.